In this segment, we'll look at the code for the second and third loops in main to finish up our discussion. So, starting with the second loop, as you can see up here in the diagram. Question 1. Identify the instructions that implement this loop. Tell which are the initializer, incrementer, and the loop test. Also, at what offset finally is toTest. So the instructions that do this are 38 through 61. And 38 through 40 are the initializer, setting toTest to 2, and the jump here indicates that down in L4 are the lines for the test, which you can see by this point pretty easily are comparing toTest at offset minus 12 to nums to test at offset minus 20, and then branching back if the result is less than. Up here where the loop body begins, and then the 3 lines between L5 and L4 are the incrementer, clearly loading toTest and adding 1 to it and storing it back, and then toTest is the last missing piece of the stack frame, which we'll fill in here in the diagram at offset minus 12 from FP. The initializer, test, and incrementer are pretty straightforward by now, but we need to look more closely at the body of that second loop, running from L6 to L5. That does an if statement, the if here in the C code, and the setup for the call of checknum sets up parameters R0 and R1, toTest and prime set per usual. So we're up here. The R0 parameter is, if you look at both steps here and here, ultimately from toTest, but the R1 parameter, sub FP 60 to R3 and then move it to R1, compare the dumbness, that's more complex. Recall that passing an array in C is really passing the address of the array's first element, and that's a pointer or address value. The sub R3FP60 computes that address to be passed ultimately via R1. Question 2 here. Reduce those first 4 lines to a single LDR and a single move. So if you think carefully about it, we still need to LDR the toTest value, but we could have just put that straight into R0, right? And then we need to get the start of the prime set array into R1, right? But we have stack pointer, SP. Don't forget that that's sitting up at the top. I'll add that to the diagram here. So this move could have been just move R1 from SP, and then we could dispense with both of these instructions entirely. Okay. The lines after the BL checknum implement the if statement based on the result of the checknum call, which, of course, recall, is returned in R0. Explain how those lines work. The answer here is that they compare the result after moving it to R3. They compare the result with 0 or false, and if the result is equal to false, then the BEQL5 jumps around the next 3 lines. Otherwise, if the result is non-zero, if it's true, then these 3 lines run, and they increment total primes. And so let's move on to the third loop now, jumping down in the diagram here, and that includes the printf that goes just before it, this guy right here. Now, the next 3 instructions, 62 through 64, implement that printf. And they are a good reminder of the LDR and SDR concepts from an earlier topic. So let's take a look at those. And of course a question on them. Question 4. The LDR for R1 is obvious enough. That's of course loading total primes as second parameter. But the LDR for R0L10 is more complex. The printf's first parameter is the string found %d primes. But in C, that means that we pass the address of the start of that string as a const character pointer. a pointer to a non-modifiable char. Printf uses that pointer or address to find the rest of the string. Answer 3 questions. How does the LDR R0.L10 instruction accomplish loading that pointer? Translate the LDR R10L10 from a pseudo instruction into the equivalent real instruction. And then finally, how could we have done the same thing without explicitly declaring or using .L10 in the dot word that follows it? Review prior lectures, by the way, on LDR, STR, and pseudo instructions if you need to. Okay, answering the questions then. The word at .L10 holds the address represented by LC0, and here's a listing of the entire .s file to see that. So going down to L10, that's got LC0 in it. LC0, bending all the way back up to the top, has the address of the string found present D primes. Okay, LDR is a pseudo instruction that maps to a PC relative LDR. And there are 31 instructions between the LDR and .L10, and no alignment padding bytes are needed. So that's an offset of 4 times 31 equals 124. The real instruction, therefore, is actually or load R0 PC, comma, pound 124. And then answering the third question, R0 equal .LC0 would have worked too. This would auto-create a word containing the LC0 address and load it so we wouldn't have to do so explicitly. Okay, so moving on to the third loop itself. That third loop is the most complex we've seen, but it builds on prior concepts, so it should be possible to decipher it fairly readily. That loop is the for loop here with its straight iteration, but this complicated test, prime set 2 test divided by bits per int and shifting and all, and that is used to determine whether we print a prime. Okay, by now you should be able to pick out the initializer, incrementer, and test pretty easily. So identify just the instructions instead that implement the loop body, just those. And of those instructions, which one implement the if test and which the if body? Okay, well, you should be able to pick off this as simply the initializer, and the body actually then begins here at L9 and extends down to the BEQ, or excuse me, extends all the way down to L8. And then of those lines, the test itself runs down to line 80 here, and the loop body is the 3 lines 81 through 83. Okay, so let's begin by looking at the if statement test here. Much of this is familiar. We saw instructions like it when deciphering set bit, the LSR, the ASL, the AND. And earlier on, when we discussed main.c, or main itself, for instance, the offset -56. Review those discussions if needed. This is question 6. And then comment, or at least explain, the loop instructions here. How do they implement the test expression? Do this with reference to the C code, and don't just use constants like 12 or 56. Again, I'm not going to comment it for you in the slide, but you should be writing comments yourself in the code at this point. Okay, so by way of explanation, then your comments should have said something like, R3 gets the value of 2 test here, and then we divide it by bits per int. Left shift by 5 is divided by 32, but that's bits per int in the code. And so we just did this computation here, in fact. And then we're going to multiply back ASL2 by 4, and that makes it multiplied by the size of an int, so we get the right byte offset into prime set. And then we're going to do a R2 points to the bottom of the locals. It's one way to look at that subtract 4 is that we would leave R2 pointing right here at the bottom of the locals. And then we will add the array offset to R2, which actually in fact drops it way down, but then we will, in the offset or in the LDR instruction, we're going to move it back by -56 so we get the right location for loading the correct index of prime set. And that's occurring on this line over here. Okay, moving on. Here we again load toTest, and we do an AND by 31, which computes the modulo of bits per int, mod by 32, leaving just that remainder. We take R2, which we just obtained from the array, and downshift it by that amount, left shift it by that amount. I'm sorry, right shift, logical shift right by that amount. And then AND in the 1, and we test to see if the resultant bit, which is the only bit that could be a 1 out of the AND, is that LSB that we shifted down, see if that one is a 0 or not. If it is equal to 0, then we branch around the if body. Now the if body is a lot simpler, but it is worth noting that there's a use of .L10 plus 4, that's a little new. The label argument in a load str pseudo instruction may include offset computations as long as the intended location is still clear. The LDR still translates to a PC relative load, in this case from the word after L10, which contains the address LC1, and that's the location of the %D string. Okay, and that completes our discussion of that second loop. The code here, if you recall, is the incrementer, and down here is the test, but they're straightforward. What we do need to look at a little more closely is the final instructions of main, and I'll show them here in C and in assembly form. In the first two instructions, the compiler is definitely being clever. Using printf to print a single character, and of course \n is just one character, that's inefficient. The putChar function, which is part of the C standard library, takes a single ASCII character as its only parameter and prints it. So the compiler passes 10 as the only parameter there, and 10 is the ASCII code for \n, and he passes it to putChar via R0, of course, and then drops the printf entirely. Now this is an example of the kind of cleverness compilers can exhibit when optimizing, as we'll see in a later topic. The last three instructions return a 0 via R0, returning from main now, tear down the stack frame, and then return to the caller, as we've seen before. But a big question here. Does main have a caller? Yes. The C compiler provides a bit of assembly that calls main, and which has an _start label marking it as the real starting point. And this assembly is the real main program, but you never see it directly. Question about it, though, just to kind of think about what it must look like, that assembly wrapper code clearly must have a BL main instruction. What two instructions are likely to follow BL main in that wrapper code? You can make a reasonable guess based on the fact that the return value of main is supposed to be the exit code of the entire program. And the answer is that we'd expect move R7 #1 and SWI 0. Remember that the return value from main will be in R0 after that BL main. Adding the move and SWI instructions ends the program with that exit code. That wrapper code is a good example of why assembly is essential. There is no C statement that can generate an SWI call. The wrapper code must be written directly in assembly. Okay, in final summary here, primes.s is a reasonably sophisticated program, and if you can decipher and follow it, you should be able to do so for most compiler-generated code if it's not optimized. And in a later topic, we'll look at compiler optimizations.